Can everybody hear me? So everybody, there will be a drinking game associated with this talk. I'll explain in a minute. But if you need a drink, go ahead and get one. I'm Wartortell, or Richard Wartell. This talk is Shellcode time. Come on, grab your friends. Basically, I was doing some work for Mandiant, FireEye, Flare, putting together a reverse engineering CTF. And this is kind of some work that stemmed out of it because I needed something to write shellcode for me. And I realized that there wasn't really that much out there that would do this work for me. So I decided to put this together and kind of try to make something that makes writing shellcode easier for you. So first of all, I have to say there is a drinking game that friends of mine play. Actually, Dual Core and his girlfriend invented this drinking game. Does anybody know Adventure Time? Hands up. Yeah, great. For those of you that don't know Adventure Time, none of this is going to make sense. So just kind of deal with that. So we're going to play Adventure Time drinking game. We're only going to use a few of the rules. First of all, there will be snails hidden. If you find the snail, everybody drinks. Also, there will be doe eyes in this. And if you've never seen doe eyes, it looks something like this. So that's doe eyes. By the way, drink. Also, in honor of this being Dual Core's drinking game, I decided that I'm going to play a different drinking game, which is every time I hear Dual Core laugh, I'm going to drink. Damn it. This is really going to bite. I'll call that another one. All right, anyway, moving on. So, first a little bit of history. We're going to cover a little bit of just how shellcode works and what you have to do to deal with shellcode and write shellcode. So first of all, shellcode is your payload. It's not your exploit. So shellcode is what you are actually putting into your exploit. It's not the exploit that you're using. So string length is exploitable, but it is not shellcode. So shellcode is what you are providing to, what you're pushing the string length to exploit it, or what you're pushing as your payload. I only bring this up because I hear this said wrong all the time, and I just want to make that really clear. Second of all, shellcode, it has to be position independent. So you have to have no requirements about where you are in memory in order to write shellcode. So for example, when you do like a normal printf call, you are pushing a string onto the stack and you're calling printf. However, if everything's moving, you're pushing that pointer onto the stack and it's a very specific address. So if things move around and you're at a different address, that's not going to work. So you have to be position independent and you have to figure out ways to handle this. Finally, shellcode is very commonly encoded or filtered. So a lot of times you are going to need to encode your shellcode in a specific way in order to use it in a certain exploit. So this, for example, if you tried to provide this buffer to string length in order to exploit it, you're going to fail. And the simplest reason is because string length will read up until a null byte. So if you have these null bytes in here, it's going to read up until then, and your payload's going to fail because in the middle of there is a null byte, so it's not going to get your actual full payload in there. Anyways, so Joe eyes, by the way. Oh, damn it. So, how do you write shellcode? The biggest thing, I mean, obviously you can write assembly, and it's a pain. So, the first thing that I want to say is you're going to suck at it if you've never written shellcode before. Like, you start going and trying to write assembly, you're going to make mistakes. You're dealing with registers, you're dealing with x86, you're actually writing the code that your processor is used to reading. It's difficult. Unless you are a computer, you're not going to be good at this, or very autistic, basically. So you're going to start out and you're not going to be good at this, but like, if you suck at it, it's okay. The more you suck at it and continue to like try, you're going to get better. There's a lot of people that are like, yeah, I tried to write shellcode and I gave up because it was tough. Yeah, it's tough. Like all the harder things in life are tough, but it's worth doing, and I would highly recommend doing this. So, first of all, assembly is really hard. There are some tools out there that make it easier to write. So if you're actually just writing assembly, go out there, look for the things that make it easier. This website is actually one of my favorite things to use in writing shellcode. It's an online assembler, and all it is a web app that will sit there and take your instructions and spit out easy bits of shellcode or different representations of it in terms of its opcodes. So it'll translate it to opcodes and make it really easy to drop into a C binary or sorry, a C program or whatever you need for it. So really, really useful in terms of writing code. However, it is definitely tough, like dealing with registers and understanding how to manipulate the stack and stuff like that is very tough. So writing assembly is definitely the harder option, but you have full control. So it's really the best option if you have a very specific need. However, there's other ways to do this. So good call, Drake. All right, so you can take shellcode. First of all, Metasploit's out there, and all of its payloads are freely available. So you can go and just rip those and use them for your needs. It's a great way to take code. Shellstorm.org is another great place that has just a database of people that have submitted bits of shellcode for different architectures, different operating systems, and it makes it really easy. So you can just shove shellcode from that into whatever you need it for. Funny story that happened to me, the CTF that I just recently wrote, I stole a piece of shellcode from Shellstorm and used it in the third challenge in the CTF. And people were completing, and when one guy says, hey, really cool challenges, thanks for using my shellcode, because it pops up a specific message box with a string that I didn't change. And he was like, yeah, I wrote that, deal with it. Damn it. All right. Another option, you can steal it. VirusTotal is out there, and you can go and just pull binaries down from VirusTotal. And if you know what you're doing in terms of doing a little reversing, a lot of things actually use shellcode payloads on VirusTotal. So go up there, find the point at which it's using shellcode, and just rip that out and manipulate it to your means. Because if you can figure out where it's providing its IP and port or whatever you're looking for, you can rip that out, change it, and use it for what you need. So there's definitely ways to steal shellcode from different sources of just malware. You know, the point of it is like somebody else has written this and they've done the work for you. You probably somebody already has created the capability that you need. So you can go and do it that way. And then finally, one of the best ways to write this is actually using a compiler to do it for you. And the incredibly smart man sitting in the front is Manifestation, who actually put together a nice blog post on how to use a compiler to write shellcode for you. So you can tell Visual Studio, hey, I need you to write you can give it options and a bunch of different things and tell it, you can tell it make position independent code, but you can tell it make small code, and then you can code in a specific way that'll allow you to do this. So I'll go over that quickly. First of all, your strings are going to be broken. So when you write a normal piece of code and you say, hey, make this local variable that's a string, it's going to put that string in the data section, and then it's going to reference that location in memory. That won't work in shellcode like we were talking about. It has to be position independent. So all you have to do is this really basic change. We refer to these as stack strings, where instead of making a string where you're referencing a character pointer, you make a character array, and then you allocate every character separately. And what you get is this. Instead of it making the compiler making a string that is referenced, it actually makes a series of pushes onto it's manipulating the string onto the stack. And then it's position independent because it's using the stack rather than a very specific address. So that's how you get strings to work. Next, all of your imports are going to be broken. The biggest problem here is, so you see this call to reg open key. It's referencing the address 404010. However, that address, if you're in position independent code, if you've moved around in memory, it's not going to be there anymore. It's going to be somewhere else. So that's not going to work. However, all you have to do is figure out where you are in memory and figure out where those functions are and fix everything for you. So you can find where kernel 32 is. There's a series of, I think, 4 instructions that will get you where the base address of kernel 32 is. You can find the export address table of kernel32.dll, and then you can rebuild all of your import table by hash. So you can do it in uglier ways by like string comparing the import address table names. There's a ton of different ways to do it, but you can rebuild your whole import address table on the fly anywhere in memory. So that's how you handle imports. And then finally, there's a bunch of different compiler options. So I'm not going to go through every single one of these. However, there's one that I want to point out because I actually had some trouble with this. This O1 option, which actually tells the compiler to make shellcode smaller. And by the way, I'm talking about Visual Studio here as your compiler, not GCC or whatever other ones. So this 01 option actually tells Visual Studio to make your code smaller. If you're using big strings, Visual Studio will start saying, I'm going to use media registers for this, and actually starts to make mistakes. So I would say be careful with that one depending on what you're doing. However, all of these definitely help to create a small, tightly packed piece of shellcode. And these are a few more of them that are just important. And then you have to do things like linking and describing where the entry point of your shellcode is going to be. So finally, how do we do this? I comically named this Wartortell because I couldn't resist. It was just too good not to. Also, this was kind of a dick move. Try and find the snail in that one. Basically, I wanted to put together a way to create shellcode and make it really, really easy to write. So the goal here is to have a simple project that you can ramp up and say, all right, I need to write this shellcode module, I need these pieces to go all in sequence, and I need everything to go really quickly and not take me hours and hours and hours of writing shellcode. Well done. I love you too, AD. All right, so I wanted to put together something that made writing shellcode really easy and also allowed you to do things like packing in sequence and doing a lot of making shellcode harder to reverse, because what we see out there a lot is things that look like this. So you have a shellcode payload, and then you have something that decodes it in like a single byte XOR or something like that. Very, very simple. So what's happening here is you have a decoder and an encoded payload, and that's all that you have. There's not that much going on there. So the second that you get past that decoder, everything becomes a lot simpler. It becomes incredibly easy to reverse, and you don't have to do that much work. So now I'm going to do a quick little demo. Doe eyes, by the way. What? Oh, thank you. There we go. Oh, I had this open. Nope. So, if we open just a simple shellcode payload in IDA, you can see, all right, this is pretty basic. There's not much going on here. It's just, you can see there's a pile of no-ops here, and then there's definitely some code going on. So the second that we turn this into code, we have this big, long no-op sled. Blah, 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 blah. And then down here, some interesting stuff. So we see a pop, a push, and then this move, and then we see basically an XOR loop. So this XOR and a loop, we can put together exactly what's happening here. And so I wrote a disgustingly tiny piece of tiny script that's all of 2 lines of code. This is all you need. If you can't see this, you're going through, you figure out exactly how long this is, and then you go through and say, okay, I'm going to decode this. So if we go, that's the wrong one. My bad, guys. I hear a dual core. So we go down here and we can see what's happened is now we actually have code. So after this, we can IDA's put together functions for us, and we can actually start going through and figuring out what's going on. You can look in here and see if anybody's ever reversed shellcode before. This is where shellcode's figuring out where kernel 32 is. And all of this becomes a lot easier, and we can start going through and figuring out everything. So at this point, reversing this is really simple. And it's even easier when you're inside of a debugger, because all you have to do is get past the decoder, and then you can watch and see it resolve imports and figure everything out. So very, very simple. I just want to make it clear that it's all it takes is like 2 lines of code for when there's a decoder this simple. And I don't like that. I wanted reversing shellcode to be a little more difficult. So what I wanted to do was put together a way where instead of you just having a payload, let's have a modular payload. Let's have a sequence of things that you know need to happen, but let's do them in such a way that things are actually packed. And each one of those pieces is packed in multiple ways so that you can't just run a single byte XOR or run RC4 or something and get past the decoded part. So let's make it this way. So the first thing that you want here we're doing kernel 32 load library, getting all the where ws2_32 is, and basically setting up everything you need for a reverse shell. Let's do each of these pieces in sequence and have the following pieces still be encoded while you're actually running these things. So how this works is the first one will be encoded, and then as things are decoding, they'll go in sequence, and you can see on the right the number of times that things are encoded. So they're encoded multiple times, different keys, different ways of encoding, so that it's not really easy to reverse engineer this. So you actually have to do some work if you wanted to go through and figure this stuff out. So that's one thing. If you have them in sequence, that's not that hard of a problem. However, you can get much more difficult. So say that I'm writing something that I don't want somebody to reverse. There's simple tricks that you might want to do, like check if you are inside of a debugger, check if you're inside of a virtual machine, and then do some benign stuff otherwise. And if you're not in either of those, then let's actually do our evil thing. How do we do this? How do we handle conditionals? It becomes much more difficult if we want to pack in sequence and have multiple layers of encoding. However, if we look at this graph, we can figure out exactly how much we can pack and what levels can pack each other. So this is the same graph as the one I was just showing you, with 1 being, is it being debugged? And 2 being, is it in a VM? And then 7 and 8 are your benign path, and then the other path is your evil path. So we have multiple paths through this. You can either, if you're in a VM, you're going to take this path. If you are in a debugger, you're going to take this path. Otherwise, you're actually going to do your payload. So what you get from that is, if every node has an encoder, we'll call it like A prime, that node can encode anything that it is in the path of always. So you'll see like number 3 is always in every path through this graph that goes to 4. So 3 can encode 4 and 5 and 6, and so on and so forth. So just to demonstrate this, so 1 can encode everything, 2 can encode 3, 4, 5, and 6, and so on and so forth. So we can figure out what can encode everything else, and go from there. By the way, doe eyes. This is the levels of encoding and how we can put all of this together. It allows us to add this different level of encoding. So I have all this working. Now I'm going to get into some of the other things that are important in terms of being able to write payloads that you would actually care about. I have not done this yet. I know how to do it though. So we're going to we need to figure out how you can put a switch statement together, because you want something like if you're writing a backdoor, you need to be able to put together a switch statement for handling commands. So how this would usually work is you would have a call to figure out which command that you have, and then you'll do a jump table that'll go to one of the different functions that handles that command. So say you have download file, upload file, reverse shell. So this is what we have. This is the code it turns into. From this, however, if we're in, if the memory addresses change, that's not going to work. That is, oh. Lemon Grab got really evil for a second there. There we go. Yeah. So anyways, when you're in position independent code, that's not going to work. That's unacceptable. So that jump table won't know where to go because those functions are in different places. So we have to figure out a way to make that work. So the way to do it is actually, this is almost correct code that I've just put up here as an example of how to do this. So you can basically put an offset table, since you are essentially this obfuscation engine, or whatever the packer that I'm putting together is functioning as the compiler. I know where the offset of each of these is going to be compared to the code that I'm writing. So I can say, all right, from here are the offsets to all of these functions. So we'll use those in order to figure out where to go. And we'll basically build an offset table rather than a direct virtual address table. And that'll solve this problem for us. So we'll have a switch statement that can go to any number of switch cases. So the next thing that we need is loops. So loops become really difficult because say that you have a sequence of things that you need to encode, or sorry, that you need to have happen over and over again. You're going to hit the decoder before every single one of them again and again. So say that you have something like I want to do some anti-VM checks. So I'm going to go to sleep. I'm going to calculate primes, I'm going to calculate digits of pi, and I'm going to go around and do this a bunch of times so that it takes like an hour, because just going to sleep isn't enough. A lot of sandboxes will say, all right, if you use the sleep function, whatever parameter you pass to it, it's now 1, so that you don't actually go to sleep in. By doing this is actually something that Fuzzy Nop and I did for a silly malware talk that we put together. This will create a really ugly loop that's going to that's just going to sit there and do some processing, go to sleep, do some processing for somewhere between 2 to 4 hours is what we did it for. And that'll evade some sandboxes pretty easily. And then after it's done that for a while, it will go and do its actual evil payload. So if you want to do this, however, with the system I'm proposing, sorry guys, this won't work because each of those is going to have that decoder in front of it, and if you go through it multiple times, it's going to try to re-decode everything. So that will break it after the first iteration of the loop. So the way to solve this is actually you have an encoder, but you have a decoder in front, but you also have an encoder afterwards. So every time that you execute one of these modules, it's going to decode it first, and then it's going to execute it, and then it's going to re-encode it so that you can treat all of them as these kind of atomic units of execution. And anytime that you need to go and re-execute one, you just have to go back to the beginning of the decoder and it'll do it all again. So how this would work is it'll decode, and it'll go through and re-encode and go through over and over and over again, and it will basically, in this scenario, it would be sleeping, calculating digits of pi, whatever, in order to evade a sandbox really easily. And so this is a great way this will solve the problem of figuring out how to handle for loops and stuff like that. So that's how we can do all of that's how we can handle all of the kind of coding constructs that we need for this. Like I said, I have some of this working. I wanted to have this code released by the time I was giving this talk. However, life got it kind of in the way. So I plan on having this released in the next week or two, hopefully. But I have most of this working except for I need to basically write encoders because I don't have the looping working yet. However, we're going to, the question is how do we make this, and how do we make this really easy for everybody to use? Because my goal here was, hey, you're a red teamer, you are writing a CTF, you need some reversing challenges. How can you make something really easily where you're going to put together this, payload that you need, and it's not going to take you that much time? So when I was writing the CTF challenges, it took me a while. Like, I was writing shellcode, I was putting all of these together, and it takes a lot of time. So I wanted to make everybody else's life easier so they could just recreate what I was doing if they needed it. So once again, this was pretty terrible to begin with. I went through multiple iterations of writing a really ugly framework that did not handle half of the things that I needed it to handle. So it's now at the point where I know exactly how to do it in such a way that it's easy for people to use, and it's clean and very straightforward, so that you actually don't technically need to know how to write code even. I wanted to make this dumb enough that if you need a CTF challenge and you don't write C++, you can still make a reversing challenge really easily. Like, I wanted it to be that simple. So the architecture is actually pretty simple. You have two main ideas here. You need to have your packers. So you need to have a description of how things are going to be encoded. So the thing that encodes each module and the thing that decodes each module. And then you need modules. So modules can be something like a custom shellcode module. It can be a very specific thing like download from Shellstorm a reverse shell. That can be a module. It can be things as simple as, I want to hide a string in memory that gets decoded at runtime so that they have to dig all the way through this ugly binary in order to get to it. That can be a module. That it'll never execute, it'll just actually jump over. Stuff like that. So the packers are basically ways to pack the code. So you have basically two functions. This is actually, you technically need to have a third function in order to support loops. But you need something to describe how to encode the data. You need something that says, okay, given whatever module I need, pass it to this function, and I will have that module encoded with this packer. You need that, and then you need something that will say how to decode it at runtime on the fly. So this is actually where the main bulk of the work here is, because it's really hard to write this in anything but assembly. So writing something that says, given a variable length packet or module, how do I pack it on the fly and then, decode it on the fly and then re-encode it on the fly. That decoding and re-encoding part is difficult and takes some time. You actually have to write that in assembly, and it's not, I haven't figured out a way to write it in C++ and make a compiler put it together for me. Because there's things like usually you need to decode the whole thing on the fly, and you have to be modifying the length that you're decoding. So you have to go through and know where the exact bytes are that you have to modify on the fly. So that writing these is a little more difficult and tends to be where the work is. And then your modules are simpler. They're things like finding kernel32's base address, or calling WSA startup, or doing some IAT, creating an IAT, doing all of that kind of stuff can be your modules. And these can be whatever you want. This is where actually writing shellcode comes in, where you need to go and say, all right, make Visual Studio write this module for me, and then I'm just going to shove it in and pack it 100 different ways, so that when it will run, but if somebody tries to reverse it, they're going to have to run through all of this stuff if they want to get to it. And then finally, The other part of this, so how I describe this is just with a JSON object. So I wanted to make this simple enough that if you pretty much tell it nothing, it's still going to create a shellcode module for you. So I basically have a JSON object that will define all the data about the shellcode blob that you want to generate, the modules you want to use, the way that you want them encoded, the code flow of the modules, and so on and so forth. And it will go and create this whole thing for you just from that. So just to demonstrate, so can we, now that's not going to show up at all. Great. This is the first example I have here, and this is how ridiculously simple I wanted to make this. It's pretty hard to see, but basically what I'm describing here is a JSON that has a sequence of modules, and every single one of them is not actually specified. All you have in there is a label for the module and what module comes next. So this, what will be created from this is a sequence of modules, and it's just going to create variable length module full of no ops, and that's all it's going to do if you don't tell it what to put inside of these. Now, rather than making all of your eyes bleed and trying to demo Ollie debug, I put together something to make this a lot easier to show. So this is the tool I put together. Basically, you have to provide the JSON file that you need for creating your module. For creating your shellcode package total. The output file also, there are different ways that you can output this. So this can spit out a C string for you. It can spit out just the binary of the shellcode, so it'll just spit out bytes. Or it can also spit out an executable. So I have been using this really crappy tiny compiler called TCC that basically I like because it does things really simply and in comical ways. And it will, this will actually go in, use the compiler to compile and put your shellcode module into a binary that you could then run. So different ways to output it. And the last thing that's listed there is a graph file. So this is entirely for demo purposes. So if we run this, you don't really see any output. However, it spit out a bunch of things, and you can see it spits out a graph of the actual code flow of this, so that you see what you're doing. If you're creating a complicated sequence of shellcode, this is going to be really necessary so that you make sure that you know where things are going and how stuff works. So if you don't provide anything, it's going to go through and create just a sequence of no ops. Like that's all that's happening here is module of no ops unpacks, module of no ops unpacks, so on and so forth. However, you can do things like here you specify the code flow of this. So you specify which node or module is the child of another module. If you do things, if you go and change one of these, it's really simple to do. And it'll update, and you can see here all I've changed is the second module now goes to the 7th, which then goes to the 3rd. And so we've just moved that one up earlier into the code flow. Really easy to do. So that's really simple examples of how this works. However, you can do more complicated things like here this is a JSON describing something like put together a module that does check for debugging and does conditionals. I haven't actually put the code in here just because to make it a little shorter for you guys to read. However, if you go and run this, you can see, really simple. So now your code flow is going to be something like it's going to check for a debugger. It's going to branch on EAX, and then it's going to either go to the reverse shell or it's going to go to something benign. So you can do really simple things like this if you want to put together, something for your red team exercise, some evil payload that you're going to use to own some company. If you say that you're writing a backdoor, you can do something like this. Like I said, this is not actually working yet, but this is what it would spit out in terms of the code flow. It'll show you. You could get your command, you could switch on EAX, and then do things like reverse shell, download file, upload file. All of that's possible. So it'll put together all of these things for you. And then finally, the last example I wanted to show is if you wanted to put something like a CTF together. Really, really easy to do. So say that you want a CTF that you're forcing somebody to go through. If anybody did the Flare-On challenge recently, the third challenge was written with this. And it's basically just making you go through and watch code and unpack things in sequence. So it's decoding a sequence of modules, and then finally, in memory will be a string at some point. Like that's all that the third challenge was, and that would take, this is all it would take to write this. So you go through and you have a pile of no-ops, and then at the very end, it's going to have a hidden key. That's all. From that, you can have, with just this tiny JSON, I can show it. You'd be able to put together this CTF challenge that says, okay, how much pain do I want them to put to go through in order to get to this key? All right, that's how many modules I want. Or I can start doing branching, doing checking for debugging, stuff like that. You could make a CTF challenge really easily with this. So that was another one of my goals with this. So anyways, this is where this is the GitHub page for Wartortell. Like I said, I haven't put it up there yet because I want it to be in a complete state for people to use by the time. So check this in the next week or two if you're interested in this. One of the other reasons I wanted to give this talk is just to get some feedback on terms of things people want to see in this. I definitely want to open this up so that people are putting up modules for other people to use and making this kind of a shellcode database that people can use and put things together easily in. So what else can we do with this? There's definitely some other options that we have here. Like I said, we can, if we can make this more of a just a well-rounded database of shellcode, it's going to make everybody's life easier. I've definitely had some times where I had to write shellcode. I assume that a lot of people that do some red team stuff or write CTFs have had to do that as well. I don't know if anybody evil is in the room, but I'm sure you've written some shellcode as well. Like, this would make it a lot easier to put together these modules and put everything together. So that was kind of my one of my main goals that I'm hoping is one of the results of this. The other thing is, I'd like to see more reversing challenges come out of this. There's writing a reversing challenge is tough. However, this gives you the opportunity to put together one really easily and in a small and tight package that's easy to pass around. So I'm hoping that people start using this to write some CTFs and do stuff like that. In terms of other things that we can do that I haven't done yet, so like I said, I don't have looping working yet, so I need to add the stage of re-encoding after. That's basically next on my list. You could also do things like say that I want a specific module to execute, and after it's done executing, I want it to zero itself out so that you have like a sandbox that regularly takes memory snapshots or something. I want to make sure that if that code isn't executing, it's not going to show up in a memory snapshot. That's something else you could do to avoid that. There's also things that we could do in terms of changing the format of how this works. So currently, I'm decoding in place. All these shellcode modules are just being decoded in sequence, and that we could change that to actually have the shellcode module copy stuff out to a buffer so that nothing is actually decoded in that one in place. You could actually have a single buffer that's just overwritten over and over and over again, and copy everything over to that. That's one different way that would probably make it a lot harder to handle because there would be a lot of switching between the two. Also, I don't have any support for filtering in this yet. That's not a crazy difficult problem. Also, Metasploit is there, so I'm pretty sure that I will be able to rip how they handle filtering, or a lot of the filtering support, and put it into this. So that's something for the future that definitely is necessary However, it doesn't exist yet. And then that's all I have, so I'll take any questions. Yeah. Yeah. So the modules will be pre-made modules that are basically just already made modules that have, it works on this operating system, this architecture. However, you can do things like I have a custom module that I want. I want this sequence of bytes. You can just specify, all right, I know what I need. I stole it from here. It goes in as this sequence of bytes inside of the JSON. Yeah. True. Yeah. Yeah, no, that'd be a great way to pull some stuff that already exists. Yeah. Sorry, so what do you mean? You were asking if I have encoders or? Sure. So I've written a couple already. So I took the easy route and wrote single byte XOR, multi-byte XOR, and just did those to begin with. And I also wrote them in multiple different ways using different registers and things like that so that it's not, you wouldn't sig on it. So how it does, you can specify which encoder you want to use. So I want a multi-byte XOR for this module. You can specify that, and then it will, if you have multiple encoders, so for those two encoders I've written multiple, it will randomly select one of them each time. So yeah, you can specify everything. I wanted it to be as simple as possible for specifying keys, specifying, you can control everything in terms of how things are encoded. So yeah, that's how I wrote the CTF challenge was, I want this multi-byte XOR key for this module and this multi-byte XOR key for this module. And then my boss told me that I couldn't have ASCII dongs in it. So, so then I had to remove all those and change everything. But yeah. Any other? Sorry? I mean, yes and no. So when they are bigger than your normal shellcode payload, I would say. So for example, one of the smallest Windows download and execute shellcode payloads is 200 bytes that I've seen. Then all I'm adding to it is an encoding loop and a decoding loop. So you're adding maybe 10 bytes to both sides of it. So I would argue they're not that much bigger. Obviously, there are going to be times where if you need the smallest piece of shellcode possible and you need it to execute no matter what, and you don't care if somebody's going to reverse it, then yeah, don't use this. Like, it would be absolutely useless for that. But in terms of actually like scaling, it's not like it's doubling code size or anything like that. It's doing just tiny bit at the beginning, tiny bit at the end, because all you're adding is just the encoding and decoding. Any other questions? Cool. Thanks a lot, guys.